All right, so before we can prove that it outputs a minimum spanning tree, we're going to need another helper. So let's consider an edge E of the graph. And suppose that we have a cut AB such that E is the cheapest edge that crosses that cut. So set of vertices over here, set of vertices over here. There's an edge that crosses the cut. We're going to say that there's an edge called E that's the cheapest to cross that cut. The cut property states that E belongs to the minimum spanning tree of G. Let's assume that this is true. We're going to take this assumption. We'll prove it later, but let's just assume that that cut property is a fact. What that means is no matter how you cut this, the cheapest edge that crosses any of these cuts has to be in the minimum spanning tree. So for example, this one, the cheapest edge would be 1, and we know that's in the minimum spanning tree. It'd be 1 again for those, 1 again for those. So let's look at something where it's not 1. For this cut, where C is by itself and the others are in another partition, well, we know the cheapest edge that crosses this cut is 4, and we know that 4 is part of the minimum spanning tree. So that's what the cut property is telling us. Our claim here is that the cut property implies that Prim's algorithm outputs the minimum spanning tree. So why is that? Well, explicitly in every iteration of Prim's algorithm, we're always looking at the cheapest edge that crosses this cut. So let me highlight a couple of points here. It's the cheapest edge that crosses the cut where U is an X and B is not an X. So by the cut property, this edge has to be part of the minimum spanning tree. Okay, so our key point here is that every edge is explicitly chosen by the cut property. And in any given iteration, the tree is a subset of the minimum spanning tree. And after termination, we're guaranteed that T is a spanning tree. And by the cut property, we now are also guaranteed that T is a minimum spanning tree. So we've proved both parts here. We've proved that Prim's algorithm creates a spanning tree and that T is the minimum spanning tree. We have a giant asterisk for this, though, and that's that we actually need to prove the cut property. So assuming the cut property is correct, we have an optimal algorithm for finding the minimum spanning tree.